class. Today we're going to be covering lesson 9.1. Now, one thing I want you to notice with 9.1 is we have different days. So we're actually going to be taking this one lesson and we're going to be splitting it up over 5 days. So there's a lot of content in this one lesson and we didn't want to overwhelm you, and so we were just trying to break it down. Now, a lot of this content is used in geometry and along with other courses. So we've eliminated a lot of the application and we've just straight focused on how do you solve these, okay? So our goal today is to be able to simplify a radical without putting them into decimals, and then also add and subtract. Okay, those are our two, or there are really 3 goals that we're going to be working on today. So first, some of you might be wondering, what is a radical? So first of all, if you kind of go down here, it says radical expression. This is what a radical is, okay? So let's just get that out of the way first, even though it's below those 2 problems. A radical is really just this symbol. Some people would call it a square root, but in the 5th lesson, we will be dealing with cube roots. So when you hear the word radical, I just want you to think of this symbol, okay? Now let's go up here. When you take the square root of 25, now if we were in class, I would ask you this: what is the square root of 25? And so hopefully all of you should be saying 5. But you also have to remember that not only is the square root positive 5, it's also negative 5. So we typically write that as plus or minus 5. Now remember, what they're asking you here is what 2 numbers, because it's a square root, multiply together to get this back. And it has to be the same number. So I could not use 1 and 25. That doesn't work because it's not the same number. So the only numbers I could use would either be positive 5 times 5 or negative 5. Okay? Now this is the correct answer. But in 9.1, so in this lesson in 9.1, we're not going to worry about this negative answer. If you want to put it, you can, but we're not going to worry about this plus or minus right now because we're going to have enough other stuff to be doing versus always putting this. Plus, in geometry, if you were given a triangle, you wouldn't have a negative side anyways. You would only keep the positive. So I just want you to know that about this one. All right, now go over to number 2. Take a look at 18. So you should be thinking to yourself, okay, what 2 numbers multiply to get 18? So your options are 1 and 18, but that's not the same. 2 and 9, but those aren't the same. 3 and 6, but those aren't the same. So if we take a look at the square root of 18 in our calculator, notice this is what we call irrational, okay? So the reason why I wanted to show you this one is because this is really the heart of the lesson. What do you do with a number like 18 that is not perfect? It doesn't have 2 of the exact same numbers unless we go decimal. So that's what we're going to work on today, okay? And down here it says simplest form. So right here, they're giving you some rules to follow in all of our problems. And so we'll kind of talk about them as we go. But this one right here says no radical has a perfect nth factor other than 1. So you'll see this one that comes up a lot of times. It just has to do with when you multiply numbers together. Like let's say we were to use like a 2 times 8. This right here has a perfect number inside it, because this is made up of 4 times 2. So that's kind of what they're talking about, is you can't have a perfect one inside. No radicals in the denominator. This does not come up, I think, until the day 3. So we'll deal with this one in day 3. And then this one, no decimals, is probably the biggest one. You just can't have decimals in any of the lessons. So that's pretty much the bigger one. Okay, so let's take a look at this one, number 2. If I know this is going to be decimal, and you already told me I can't have decimals, well then what am I supposed to do? What you want to do is you want to look for the combination. So which of these combinations has a perfect number in it? So let's quick talk about the perfect numbers. So if you think about 1 squared, you get 1. We don't usually use that one because it's not super helpful, okay? So now think about what is 2 squared? What is 3 squared? So it tells you to list the first perfect 10. So let's do that right now. So we've got 1 squared, 2 squared, 3 squared. So now we're going to go 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared. Now, I'm not telling you have to have these memorized, but knowing these numbers is extremely helpful. So some people like to write them on an index card so that way they can just set them, like by their homework problems. That way it's a quick reference. So now looking at these numbers, okay, so looking at this set, if we eliminate the 1, so if we look at this set of numbers, which one of these numbers falls in our 3 combinations up here? So if we go through, the 1 in the 18 doesn't work. The 9 is perfect. Notice the 3 or 6, neither one is perfect. So what we want to do is we want to think of the square root of 18 is really 2 times 9. Now, the square root of 2 is also pretty ugly. So if we look at the square root of 2, it's what we call irrational. So we're just going to leave the square root of 2 alone. We're just not going to touch it. But what is the square root of 9? So hopefully you know that one because it's also listed right here on my paper. So it's 3. So do you notice how this one is what we call rational? There's no decimal behind it, okay? So we bring this one out front. So the square root of 9 was 3. And now that is your answer. Okay, so let me show you on the calculator. The calculator cannot do these for you, but you can definitely check your answer to see if they work. So do you see how they're the same decimal? And what this reminds me a lot of is when you first started doing fractions. So at whatever age you learn fractions, probably somewhere around 2nd or 3rd grade, you might have been given a fraction like 5/10. And so you were asked to reduce. So when you reduce this, you're still left with a fraction. It doesn't reduce to a whole number. It's still a fraction and a fraction. But these have the same decimal value. You're doing the same thing here. You're taking the square root of 18 and you're just reducing it to 3 square roots of 2. Notice fraction, fraction, radical, radical. So it's very similar to what you did with fractions, only you're learning a new concept here. So this is what you're going to be doing for the majority of the lesson, is you're going to be thinking of the combinations that make up the number underneath, looking for a perfect one. Okay, so let's try another one together. So number 3, we've got 12. So if I think of, and you don't have to write this down, you usually just kind of think of it in your head, all the combinations that multiply to get 12. So notice those are the different combinations to get 12, right? Well, this one isn't going to help us because besides 1, 12 is not perfect. Neither one of these two are perfect, but 4 is perfect. So what we're going to do is we're going to think of this as the square root of 3 times 4. Now the square root of 3, notice it's not listed up here. So the square root of 3 is going to be pretty nasty. It's going to be irrational again. So we're just going to leave that one alone. So we have, oops, I shouldn't have put it equals there. Here, let me start over. The square root of 3, we're just going to leave that one alone. And because 4 is perfect, we're going to take the square root of 4, which gives us a 2. And then that is our answer. Okay? So why don't you pause it here and quick try 50. All right, hopefully you tried 50. The different combinations are 1 in 50, 2 in 25, or 5 in 10. Those would be your different combinations. But again, if we go through our process, this is not perfect. Ooh, this one's perfect. And this one is not. So we're going to use this as 2 times 25. The square root of 2, we already saw, is quite ugly, so we're going to leave it alone. but because the square root of 25 is perfect, it comes out front and we take the square root. And so then this would be our answer, okay? Now, before we move to number 5, I want you to know that when you take the square root of 25, you're really doing 5 times 5. Do you see how there's a pair of them? That's why 1 comes out. When you're doing the square root of 4, that's really 2 times 2, and that's why 1 of them comes out. So we're going to do the same thing over here because now we have a variable, okay? But let's look at the number first. So 24. So you have what? 1 and 24. You have 8 and 3. And you have 4 and 6, correct? It really helps if you know your multiples. So no perfect, no perfect. There it is, okay? So you want to think of this as 4 times 6. Now the variable we can just put right there for a second. So the square root of 4 is perfect, so it's going to come out front. Now I'm going to leave a little space here because I have these letters behind it, okay? So I'm going to leave a little space, and I'm going to say the square root of 6. Now g's. You're trying to take the square root of g to the 6. That is really the same thing as 1, 2, 3, 4, 5, 6, correct? So remember what I showed you with the square root of 25. In square root of 25, that's really 5 times 5. So because you have a pair, basically that pair gets to come out of the symbol like that. Now, in the case of 25, you don't have anything left over. These are gone, so then it would be like a 1 is left, and then we don't have to worry about that. So we need to look at this and ask ourselves, how many pairs do we have? So here's our symbol, okay? And every time we have a pair, we're going to pull one out. So we have 1 pair, we have another pair, and we have another pair. Notice all of the pairs have been used up, so there really is nothing left. And so what we're left with outside is 3 of them. So on this piece, notice because I've got 6, which is 3 pairs. And then that would be my answer. Okay? So you want to think of variables just the same as you would with numbers, with whole numbers. Okay? Now notice we only have 11 problems to try, but I definitely think I would like you to try one on your own. So if you can't see this very well, it's 48h to the 7th. So go ahead and give that one a try. Now, let me tell you the answer because I personally think this one's a little tricky. So the correct answer to this one is -4h cubed over 3h. That would be the correct answer. Anything else would get marked down. Now, 48. We got to think of the multiples of 48. Okay, so 48. Obviously, we have 1 and 48, but are you guys okay if I just don't write that one? Okay, so 1 and 48. We have 2 and 24. We have 6 and 8. We have, 3 and 16. We have 4 and 12. I'm trying to come up with the multiples here. This one is the one I usually go with, so that was the one I thought of first. And I think I've got them all, okay? All right, so let's take a look at this one. Neither one of these two is perfect, so we can get rid of this option. This one is also not perfect, so we can get rid of this option. We've got a perfect here, and we have a perfect here. So now the question falls to which one do you use? And if I could tell you, you always go with the larger perfect. So I'm going to show you this option first, but I will also show you this, but it's much, much more complicated because what's inside of 12? 12 is also 4 times 3. So do you see how there's a double perfect? So I will show you that combination, but it is harder, okay? So let's go with the 3 and the 16. So the square root of 3 And it doesn't matter which number you write first. If you would have wrote 16 times 3, that doesn't matter which one comes first. That's the commutative property. So the square root of 16 is 4. Now think about your h's. If you think about your h's here, you have 7 of them. There's 7. So ask yourself, how many pairs do you have? So you've got 1 comes out, another one comes out, and another one comes out. And then do you see how this guy is left over? It does not have a pair. So that one stays under. Now, if I didn't explain this, this is back from chapter 6. How do you write this? You write this as h cubed. The 3 is an exponent, not a coefficient, okay? So make sure you're writing that properly. That is from chapter 6. So now I've got h cubed out with an h left under. And that is the correct answer. Now, I'm going to show you the other way, or the other combination. The other combination is harder. So if we use the combination, and let's just think about the square root of 48. Let's not worry about the letters, because the letters are not going to change. So the square root of 48, if we think of it as 4 times 12, like that. The square root of 4, I do not disagree, is a 2. So that comes out as a 2. And then you'd be left with 12. And that's not really wrong, but it fails your rule right here. It fails this first rule, that you still have a perfect other than 1. So you still have a perfect number hidden here. So now you have to think of the 12 as 4 times 3. And so we have this original 2. And now what is the square root of 4? So the square root of 4 is 2. And then the 3 you can't do anything with, so you leave it alone. And then you multiply these together. I know in this case it doesn't matter because 2 plus 2 and 2 times 2 are the same. However, it will make a difference when you use different numbers. So you want to watch for that. So what I would tell you to do is when you list your combinations, always go for the largest perfect number that you can. If you use the smaller one, it's going to require more work on your part, okay? So why don't you try numbers 7 and 8, and then don't go any further because notice we have addition down here. So go ahead and pause it here and give those a try. All right, so hopefully you paused it. On number 7, I would be using the combination of 2 times 81. That's what I would be using for my numbers. So the square root of 2 is not very nice. We're going to leave it alone. And then the square root of 81 is just plain old 9. So we're going to bring that out front. And then if you notice, I left a little space for my variables. Okay? Now, look at your first variable, f. F does not have a pair. There's nobody to pair him up with. So the f is going to stay under. Now take G. G has 10 of them. How many pairs are there with 10? So if you have 10, that would be 5 pairs. And they're all gone. So 10 divided by 2 is 5. And then there's no G's left under here. And then this would be our correct answer. Okay? There's no way to test the letters, the variables in your calculator. You can test the numbers. So like watch the square root of 162 and then 9 square roots of 2. Do you see I can check the numbers, but I can't check the letters in my calculator. And so you just got to know that. All right, number 8 for 512, I would have been using 256 times 2. And that's a hard one. You might not recognize 256, but if you take the square root of 256, notice it's 16. So let me write that down, and then I'm going to show you one other kind of little trick that can help. So I've got the 2 is going to stay under, and then the square root of this is 16. And notice I'm just kind of leaving a little space to do my letters in a second, okay? So one little trick sometimes with perfect squares is if you go to your y equals, and if you have anything in here, go ahead and clear it out, and then just type in x squared. Just single x squared. You don't have to put anything in any of the other equations. And then instead of graphing it, go to table. So go to second table. Now you might have to mess around with your table for just a second because do you notice how mine is actually right at the one we wanted? But if you just scroll your table up, so I'm just trying to get it back to 0, just to kind of show you. Notice 0 squared, 1 squared, 2 squared, 3 squared. So these are all your perfect squares. So if you want to go above 10, notice the calculator, it'll keep going. It'll tell you, 17 squared, 18 squared. It'll just keep going for you. So sometimes this is a nice fast way to generate the list. Okay, so you go under your y equals. All right, now let's take a look at the letters. We have x cubed. So again, remember what that is telling you. X cubed, 1, 2, 3. So you have one pair that gets to come out. And then notice this guy doesn't have a pair, so he's stuck alone. So in the pair, only one comes out. Okay, so we're going to put one out and one under. And now think about your 9. You have 9 of these. And hopefully you're kind of starting to notice a little pattern. You're always pulling them out in pairs. So if this is an odd number, you know there's going to be one guy left over. So you know this one is going to be under because it's an odd number. So now you have 8 of these left. How many pairs are inside there? You should be saying 4. There's 4 pairs. Okay, so then this would come out as y to the 4th, and then we have a y left over. And then that would be our answer. Okay, so this is what we call simplifying. This was our first goal of the day. Our second goal is to know how to add and subtract, and it's actually easier than what it sounds. Radicals behave just like variables. So if I were to give you 3x plus 3x, as long as the variable parts are the same, you would just add the coefficients together like that. So what we want to do is we want our radical part to be the same. Now this is a plus sign if you can't see on the projection. Remember, we don't have any divisions, and we actually will have divisions later, but they don't use this symbol. They do them as a fraction. So we need these two to match. Now 2 is prime, so it's not going to go any lower. But we can get the 8 to go lower. The 8 is made up of 4 times 2. So we can break the 8 down. So the square root of 4, that just comes out as 2. And then this guy is left alone. So this right here is simply the square root of 8. Just the square root of 8. But I got this guy sitting out front. I got this 3 sitting out front. That's no big deal. You just multiply them together. So this would be 6 square roots of 2. And then now this one, remember, we said it can't go any lower because it's prime. So we're just going to kind of trickle it down here. So 3 square roots of 2. And then notice now how my radical pieces are the same. So I've got a square root of 2 and a square root of 2. So what I do is just combine my coefficients. So I go 6 plus 3. And then the radical does not change. Just like you did not change the variable over here. Okay? You're simply combining the coefficients. And then this would be your answer. And again, if you want to check it in your calculator, you can. You just got to be careful when you type it because in my calculator, watch my symbol bar, watch my radical bar. If I try to go plus 3, do you see how my bar continues? So I have to be very careful when I do this. Once I type the square root of 8, I have to use my arrow key and I have to arrow over to get my little radical to stop. Some of you who have an older style calculator, which I don't have one here, but when you type the square root, it'll put a parenthesis. You're going to have to make sure that you close that off before you do your plus sign. okay? Every model calculator sometimes can be a little different. So you have to learn the model that you're using. So notice that was the original, and so I'm just going to get the decimal answer. And now I'm going to type in my answer, 9 square roots of 2. See how they're exactly the same. Again, it reminds me of when you were younger and you were adding 1/5 plus 2/10, or not even 2/10. How about we go 3/10, because that would make it a little harder. You'd have to get a common denominator in order to add these together, but your answer would still be a fraction. You're doing the same thing here. It's not called a common denominator, but you're trying to get your radicals to match, just like you have to get denominators to match. So this lesson is very similar to fractions. Okay, why don't you try number 10? Even though it's 3 parts, why don't you pause it and give it a try on your own? Okay, hopefully you tried number 10. The one thing I'm noticing right off the bat is this one is prime. So this one's not going to go any lower, but these other two are going to need some work, okay? So 18. 18 is made up of 9 times 2. So what I'm going to do is I'm just going to work on this one for a second. 9 is my perfect square, so that's going to come out as a 3. This is left under, and then I still have this 2 out front. And we always multiply, okay? So this is really 6 square roots of 2. Make sense? Okay. Now the second one here, we've got a minus 2, and now we've got the square root of 20. So the 20, I'm hoping you're coming up with a combination of 4 times 5. So I'm still going to copy this minus 2. This is just coming straight down. And now, if you take the square root of 4, that's going to come out. So the square root of 4 is 2. And then the square root of 5, you can't do anything with. And then we multiply these together. So that would be, so if you multiply those together, that would be a negative 4 square roots of 5. Now notice what we said on the end. This one is prime. There's nothing you're going to multiply with for 5 except for 1 and 5. So you don't have to do anything with that. So we're just going to kind of take this one and carry it all the way down. So minus 2 square roots of 5. Okay? Now, pause for 1 second. Let me grab my piece of paper here. If I were to give you a problem that looked like this. You see that problem? Because these variables are different, you would not be able to put them together. But because these variables are the same, you would combine them. So you would tell me 3x minus 6y, correct? And then you just would be done. You're going to do the same thing here. Do you see how this radical is different? But do you notice how these two are the same? So what you're going to do is you're going to put those two together, and you're going to leave the one that's different alone. And just like we did with the y's, we just copied it down. We didn't change it. We're not going to change the 5. We just recopy it down, okay? So if you're feeling comfortable, you're more than welcome to go ahead and try the practice problems. If you would like, I'll go through one more, and that's the only thing I have left to do. So again, if you feel pretty comfortable, go ahead and try the practice problems now. All right, I'm going to go through one more on number 11, just in case anybody needs help. You are welcome to pause the video and try it first, or if you just want to see me do it, you can do that too. And again, on the projection, it might be a little bit hard, but these are both plus signs, okay? Remember, we're not going to have any division right now. This one is a little difficult because notice all 3 of them can go lower. So this is a lot of work, so I'm going to use up a lot of space here, okay? So first one, I'm just going to take it one at a time. First one, I've got this 3, and now I'm thinking of the 12. So I'm going to use the 12 as 4 times 3. And so my square root of 4 is just 2. The square root of 3 is not very pretty. And then I have this one out front. And so I multiply those together, and that's what I've got. So just take it one piece at a time, okay? All right, how about the middle one here? So same thing. I'm going to go plus 3, and now I have to think of 18. So 18, I'm going to use 9 and 2. So I'm going to write down the plus 3, and then the square root of 9 is 3. So I'm going to go times 3. And then the square root of 2 here is not very nice, so I'm going to leave it alone. And now I'm going to multiply those together. So 3 times 3, and then I don't do anything with the square root of 2. Makes sense? So I've done the first and the second, and now the third. So I'm going to do plus 2, and then I have to think of the 27. So 27 is going to be 9 times 3. And so I'm going to copy my plus 2, so that's just going to come straight down. Now my square root of 9 comes out, so that's just 3. And then this is not very nice, so it's going to stay under. So if I multiply that together, remember you got to multiply. 2 times 3, and then square root. And then what I'm going to do is I'm going to look through this, and I'm only looking at the radical. So I'm just looking at the radical. And so what I'm noticing is the first and the last are actually the exact same thing. But it's more important is that the radical is the same. I really don't care that these numbers are the same. That's just a nice coincidence. So I add 6 plus 6. The radical does not change. And then this one didn't have anybody to combine with. And so we just copy it down like that. And it really does not matter which of these come first. If you would have put 9 square roots of 2 first, that does not matter because it's the commutative property, okay? So either one would be perfectly acceptable. If it's in a multiple choice, only one would be listed. They could never list both, and it's just kind of a matter of who the author is. It just depends on who's writing it, okay? So that concludes 9-1, day 1. Now, can you imagine if we would have tried to do more material? So we're going to do this over the course of 5 days. There is that much content in this one lesson. It's just absolutely crazy the amount of material that they tried to squeeze into one lesson. So we're going to take our time here, okay? And as always, please ask if you have any other questions.